Forget heavy particle systems or hunting for texture assets. With just a bit of code, we can calculate infinitely precise interactive effects using WebGPU. It's not just high performance, it's pure logical beauty. Many find shaders difficult because bridging CPU logic to the GPU is hard. But today, we break that barrier. We'll build TSL nodes like Lego blocks and drive the graphics card directly with React click events. After this, your 3D scenes won't just be static images, they'll be alive. I use the RAFCE snippet to quickly generate the component structure. Then I swap the container for a canvas. Thanks to VS Code's auto import, the dependencies at the top appear automatically. Here's the key point. The default canvas uses WebGL, but since we're working with TSL, we need to manually take over the initialization. Inside the GL prop, we use async and await to initialize the WGPU renderer. Notice the top of the file, 3/WGPU is imported automatically as I type. Set the element to position absolute with inset to 0, so it fills the entire screen. Give it width 100% and height 100% to ensure full screen coverage. Use a dark background color like #111 to create a dim room environment, so when the halos light up later, the contrast will be maximized. A common beginner mistake is listening for clicks directly on the background. Instead, we need a dedicated interaction layer. I'm creating an interact plane and passing on pointer down to the mesh. Its sole job is to tell us where did the mouse click. If you set visible to false, Three.js raycasting will ignore it. So the trick is keep it visible, but set opacity to 0 and make it transparent. Now it's invisible, but still clickable. Back to the main component. We need a rings array to store the active rings and an ID ref to assign them unique IDs, preventing any key conflicts. Next, the interaction logic. Inside handle pointer down, the first thing we check is e.uv. If the raycast didn't hit a UV coordinate, we missed our target, so just return. Here's the key. We destructure X and Y directly. Compared to world coordinates, normalized UV data from 0 to 1 is much easier to handle in shader math. Finally, we package the ID and coordinates into the array. The logic is complete. Don't forget to mount it onto the interact plane. This ensures that our invisible floor can actually capture mouse click events. Think of every ring as an independent entity. It has its own birth location, center UV, and its own moment of death, on done. Here is a crucial concept. Why use uniform 0 instead of props? Because shaders run on the GPU, while React runs on the CPU. We need the uniform as a data pipeline to push new data every frame without recompiling the shader. Let's start drawing. We place the TSL node construction logic inside useMemo, so it's built only once during initialization. First, calculate the distance d from the current pixel's UV to the click center. The length function handles this. It's like drawing a cone centered on the click point. How do we turn that cone into a ring? First, define the thickness and the feather value for softness. Calculate a half t, half of the thickness as well, so we can immediately compute the inner and outer radii. We use smooth step twice. First cut, Outer, defining the outer edge. Second cut, inner, defining the inner edge. Subtract inner from outer, hollow out the middle, and what's left is our ring. Combined with the feather parameter, we get those soft, anti-aliased edges. To see the result, we need to render the mesh. Note that since this is a WebGPU material, we must register it with extend first, otherwise R3F won't recognize it. After registering everything, return the mesh and attach the nodes. Important: enable transparent and disable depth right. This ensures that when multiple halos overlap, they blend smoothly instead of blocking one another. Then, in the main component, map through the rings array to actually create the ring instances. Since we haven't written the animation yet, the radius is 0. We have the shape, but we don't want them all to be the same color. Let's pass in a random hue seed and use TSL's MX-HSV to RGB function. We define the HSV, lock the saturation and value, and just rotate the hue. This way, no matter what random color we get, it's always a bright neon. Now each ring has its own personality. A standard ring looks flat. To give it some energy, we calculate a T-band. This represents the pixel's relative position within the ring's thickness. Then we linearly interpolate the brightness. Super bright on the inside, 2.2x, slightly dimmer on the outside. It makes the ring look like it's glowing from the core, not just a texture. Final compositing step. Multiply the base color by brightness, then by 2.0 for extra pop. Also calculate alpha. Multiply the mask by 1 minus fade so the ring fades out over time. Here is a critical fix. We must update the return object with our calculated final RGB and alpha. If we don't do this, the brightness and fade effects won't apply. Now we need to drive those two uniforms inside the useFrame loop. First, accumulate the elapsed time and clamp the progress t between 0 and 1. Use let here because we're about to modify it. I don't want a rigid linear animation, so I rewrite t using a cubic ease-out formula, 1 minus 1 minus t cubed. This mathematical trick turns uniform motion into a curve that pops open with a snap. Assign the calculated t to radius.value. I multiply by 0.5 to limit the maximum size, otherwise it gets too big. Next, set fade.value to t as well. Notice the dot value. This is what I mentioned earlier. We calculate the curve on the CPU and push it to the GPU via the pipeline. Assigning directly to radius won't work. For robustness, we need a done ref flag. Watch this. Add a guard clause at the start of use frame. If the ring is finished, return immediately. This prevents extra calculations when on mounting, a great performance habit. Now handle the lifecycle at the bottom. When animation progress t is greater than 1 and it's not marked done yet, the ring's life is over. Lock doneRef immediately, then call onDone. I recommend the optional chaining ? Syntax.
If the parent component forgets to pass this function, the app won't crash. Safety first. One more newbie trap. The generated ring is also a mesh. If you don't handle it, new rings will block your mouse clicks. So you must set raycast equals null on the ring mesh. This tells Three.js, ignore me, let the ray pass through, allowing us to generate rings continuously.
The hardest part of writing shaders isn't usually the math, it's tweaking parameters. To help you get a feel for it, I've deployed this entire demo to goodtsl.com. Look here. No need to constantly code, save, and refresh. Want a thinner ring? Drag thickness. Want harder edges? Reduce feather. Once you've tweaked the perfect parameters in the GUI, the code is already generated. One click to copy, paste, and use. The time this tool saves you should be just enough to hit that like button, right? Let's summarize the architecture. The bottom layer is an invisible interact plane. The top layer is a list of dynamically generated rings. React handles life and death. TSL handles light and shadow.
See, once you bridge the gap between React and TSL, you're not just creating a ring, you're building an entire interactive visual language. If you found this Lego-style shader approach inspiring, please drop a like. It helps the algorithm share this with more developers struggling with shaders. Links to the source code and good TSL are in the description. Give it a try. You'll find WebGPU
isn't so scary after all. See you in the next one.